Okay, we are continuing right along with the June 2019 exam. We are now on the answer booklet. Why? Because we have moved on to part B2. And B2 is the first section where you are going to be required to write your answers here in the answer booklet instead of in the test booklet. Now you can write as much as you want in the test booklet, but it's not going to be graded. The only thing that gets graded is the answer booklet. Okay, so I like to make a lot of notes in the test booklet, but I have to transfer my answers to the answer booklet. All right, draw a structural formula for methanol. All right, this is a reference table. So what I'm going to do is just make a note here that what I'm drawing is this. And I'm making sure I wrote that correctly because that is what's important. Okay, so where do I go for my reference table? First, I go here. Meth is 1 carbon. So I'm going to put 1 carbon. Now I'm going to go to table R and I'm going to start looking through the examples and look for an ending that matches. This says ane, no. This is close, not quite. Nope, aha. So it's an aldehyde. So what I need to do is make the last carbon. How do I know it's the last carbon? This doesn't have an address. Look like this, the functional group. Now I only have 1 carbon, so all I have to do is on that carbon make it look like what it said for the functional group. You could put an H here or not, so like this, just to be sure. Okay. All right, let's move on to the next question. I can skip, now it says right here 52 through 54 are based on this. So I'm going to skip this reading and skip this reading for now and go to the question first because sometimes I don't need it, so we'll see. Explain in terms of subatomic particles. Well, my options for subatomic particles are protons, neutrons, and electrons. Okay? So my answer has to talk about one or more of these. Why atoms of H1, H2, and H3 are electrically neutral? Well, electrically neutral means it has a charge of 0. So that means whatever it has that's positive and whatever it has that's negative have to be balanced or equal in order to get electrically neutral. So according to this, protons are positive, neutrons have no charge, and electrons are negative. So I'm going to use that to write my answer. Okay, so explain in terms of subatomic particles why atoms of H1 and H2 are each electrically neutral. The atoms are electrically neutral because they have equal numbers of protons and electrons, the positives and the negatives. So I mentioned subatomic particles and I explained it. So I followed the directions of the question and what I wrote is true. You have to get points for that. Okay. All right, now let's look at the next question. Determine the formula mass of heavy water D2O. Okay, so here we have the isotope H2, also called deuterium, is usually represented by the symbol D. Heavy water forms when deuterium reacts with oxygen, producing molecules of D2O. So D2O, the D refers to H2. So I need this. Okay, so how do I find formula mass? I find formula mass by adding up all of the masses of the elements in the formula. So I have 2 of these. Well, what's the mass of this? Well, it rounds to 2. So 2 times 2. Why 2 times 2? Because there's 2 of them. Plus, well, I know the atomic mass of oxygen, but let me just show you where you get it. If you do forget this one, you should know we use it so much. But it's this, which rounds to 16. Okay, and 2 times 2 is 4, plus 16 is 20. So, on my answer booklet here, 20. Okay. Based on table N, all right, so I'm going to go to table N, identify the decay mode of tritium. Well, which one is tritium? It says right here, tritium, H3. So I go to table N, and I start looking for H3 right here. What is the decay mode? B minus. So I could write that. But if you look, that's beta, so it's beta decay, B minus. Okay, I have a few options of what I could write. So B negative, beta decay. Okay, I could write either of these. They would be correct. I could also have written the symbols, right, from table N, because it says my answer comes from table N, so I have a lot of options, because I could write this and then use in conjunction with table O to write a lot of the options there. Okay, all right, let's move on to the next question. So I'm going to have to turn this page, flip this one. Okay, here we go. Oh, I got a couple of short answers. Maybe that means they're easy. Let's see. So I'm going to look here. It says 55 through 57 are a group. I have this, but let's see what I need. Convert the temperature of NaNO3 to kelvins. Okay, so here's my temperature. Now, I know how to do it easily. This one is actually an easy one because it's not a negative, but we have this formula. So here's how I recommend you do it. K equals degrees Celsius plus 273, right? My Celsius temperature is 23, so K equals 23 plus 273. And then, just to be safe, you put it in the calculator. 23 plus 273. Don't make silly adding mistakes. And then you see the answer, 296. So that is what I put right here, 296. Okay, based on table G, determine the additional mass of NaNO3 that must be dissolved to saturate the solution at 23 degrees Celsius. All right. So again, it literally said table G. You better turn to table G. So let me open up table G. Solubility, and I'm talking about NaNO3 at 23 degrees Celsius. So NaNO3's line starts way up here. But luckily, I'm only dealing with a low temperature. So again, this is NaNO3's line right here, this one. I'm at 23, so a little bit less than halfway. So you can see right here. At 23, to be saturated, I need 90 grams. Okay? So I need 90 grams to make it saturated. But did I add 90 grams? No, I did not. How many grams did I add? 85. So the question is not asking how many grams do I need to add. So I don't want to write 90. How many more? So if I added 85 and I need 90, how many more do I need? 5 grams. Okay. Now for this question, I'm just going to tell you, you had a little bit of leeway. On our key, it said we could take anywhere from 4 to 6 grams. Okay, so I said it was 5, but if you said 4 or 5 or 6, you were still right. Okay. Say what happens to the boiling point and freezing point of the solution when the solution is diluted with an additional 100 grams of water. Okay, so when we add something to water, the boiling point goes up and the freezing point goes down. Boiling point's a high number, it goes up. Freezing point's a low number, it goes down. But if we add more water, we're going to reverse these effects, right? So the boiling point would actually decrease and the freezing point would increase. Okay? All right. Now we're on to our next group of questions, okay? A 200 milliliter sample of CO2 gas. So I'm going to go here. State a change in temperature and a change in pressure of the CO2 gas that would cause it to behave more like an ideal gas. Well, in an ideal gas, the particles are far apart. So how would I change pressure to make them far apart? I would decrease pressure. All right, what else about an ideal gas? Ideal gas particles are very small. There's no intermolecular forces. They're moving rapidly. Oh, moving rapidly, you say? Okay, in straight line motions, but the rapid part is what I'm focusing on. In order to make them move rapidly, what would I do to temperature? Well, you know, I would increase temperature. So I would increase temperature and I would decrease pressure. Okay, next one I'm probably going to do a calculation. So let's see. Determine the volume of the sample of CO2 gas if the temperature and pressure are changed to this and this. Okay, so I'm dealing with a gas. I have a bunch of temperature, pressure, volume. Can you guess? Do you know what you have to use? You got it. The combined gas law formula. So I'm going to do my notes down here. P1 V1 over T1 equals P2 V2 over T2. So let's go to the question and let's get our initial numbers. Okay, so I need values for P1 V1 T1, P2 V2 T2. So V1, 200 milliliters, 296 Kelvin, and 101.3 kPa is changed to 336 Kelvin, 152.0 kPa, and what is it? All right, so plug in my numbers. 101.3 times 200 divided by 296 equals 152.0 times V2 divided by 336. Now, a lot of times they're just going to ask for this setup, but in this case, they're not. They're asking you to solve it because I need to answer in milliliters, okay? So I'm going to cross multiply, okay? So I'm going to get 101.3 times 200 times 336 equals 296 times 152.0 times V2. All right, so I think it's easier if you get those numbers first. So that's what I'm going to do. 101.3, right, times 200 times 336 equals 6807360 equals, let's do 296 times 152 equals 44992. 44992 times V2. How do I solve for V2? Well, I divide both sides by 44992, which will give me V2. So I got to re-answer this. 6807363 divided by, see what I've entered there? Okay, divided by 44992 equals 151.3. V2 equals 151.3. I've got three significant figures up here, so my V2, 151 milliliters. Okay, and now I need to put that in my answer booklet, right? 151. All right, now for 60 and 61, it looks like I have more to write. So let's go back to those. State in terms both the frequency and the force of collisions. So I have to talk about both. So frequency is how often, force is how strong. So I have to talk about both things. What would result from decreasing the temperature of the original sample of CO2 at constant volume? Well, if I decrease the temperature, that's decreasing average kinetic energy, which means the particles are moving slower, so they're going to collide less often and with less force. Okay? The particles would collide less and with less force, right? So the particles would collide less and with less force. Okay. Last question for this section. Compare the mass of the original 200 milliliter sample of gas to the mass of the CO2 sample when the cylinder is adjusted to the volume of 100 milliliters. Well, let's see. It says up here, it is placed in a sealed, rigid container with a movable piston. So that means it's like a syringe, right? So I can have the piston way out like this, or I can push it way in like this. But it says it's sealed. So that means nothing's getting in or out. So if nothing is getting in or out, oh, the masses are equal at both volumes because it's a sealed container. So nothing is getting in and nothing is getting out. So the masses are equal. They're constant. They stay the same. Some way you had to say that. All right, so now let's flip. We are almost done. We have one more section in B2, and it's this. Okay, here's our last one, 62 to 65. Again, we're going to skip this at first, and we're going to go to the question. Explain in terms of both protons and neutrons why cobalt-59 and cobalt-60 are isotopes of cobalt. Well, you should know the definition of an isotope. They have the same number of protons, but a different number of neutrons. Okay, so cobalt-59 and cobalt-60 are isotopes because they have the same number of protons, but a different number of neutrons. That's isotope definition. You should just literally just know that. That should not be a question. That should not be hard. Okay? Compare the penetrating power of beta and gamma emissions. Okay. Here's what you should remember. So I'm just going to show you table O real quick. All right? What penetrating power has to do with is both mass and charge. Okay? So the two that I'm comparing are beta and gamma. If you have a bigger number on top, you have less penetrating power because you have more mass. Okay? If you have a number on the bottom, you have less penetrating power compared to like a 0 on the bottom because you have stuff in the way. Okay, so first we're going to look at mass, then we would look at charge. Okay, so if I was comparing these two, automatically I know the alpha would have less penetrating power because it has a bigger mass. All right, so I'm comparing beta and gamma. So beta and gamma. Well, they both have 0 on the top, so mass doesn't play a role. But then if we look at the bottom, gamma has 0 and beta has a -1. So that means the beta particle has less penetrating power. So that's what I need to write here. Beta particle has less penetrating power. Okay. All right. Let's go on. 2 questions left here. Complete the nuclear equation in your answer booklet for the decay of cobalt-60 by writing a notation for the missing product. Okay, so what has to happen is the number on the top on both sides of the equation have to be equal. So I have 60 on this side, and so far over here I have 0 and 0. So that must mean I need a 60, right? On this side I have 27. On this side I have -1 and 0. So how do I get both sides to equal 27? Well, I could set it up like this, just so you know. 27 equals something plus -1 plus 0. Well, the plus 0 doesn't really matter, right? So 27 equals x plus -1. Add 1 to both sides. So when it's a negative, you got to be a little careful. So it's 28. But now I need a symbol. Where do I get the symbol from? Well, go to the periodic table, and I'm going to look up 28, nickel. Okay. All right. Now, based on table N, so I know I need to look there, but let's read the rest of the question. Determine the total time required for an 80-gram sample of cobalt-60 to decay to only 10 grams of the sample, until only 10 grams of the sample remain unchanged. So I started with 80 grams. What does table N tell me? So let's go there for a second. Table N tells me half-life. Okay, cobalt-60. So let's look it up. 5.271 years, right? 5.271 years. That's its half-life. Okay. So if I start with 80 after a half-life, 5.271 years, I would have 40 grams. Well, I need to go until I have 10. So then another half-life occurs, right? And then I have 20 grams of my original sample left. Not enough. Then after another 5.271 years, I have 10 grams left. Oh, finally I got to enough. So it went through 1, 2, 3 half-lives. Remember, for half-lives, you don't count the numbers because that's just our starting point. We count the arrows. I wrote the half-life above the arrow to remind you. So what I really need to do is take 5.271 times 3, right? So I could do it in the calculator if you don't want to make a mistake. There's my strong suggestion. 5.271 times 3 equals, and then I'm going to write this as my answer. 15.813. Okay? 15.813. All right, there we go. That is the end of B2.